Hello, everybody. In this lecture, I'm going to be talking about the chemistry of polymeric biomaterials, specifically the degradable biomaterials. And often when we talk about degradable biomaterials, we mean hydrolyzable. That means that they're going to be degraded as they are exposed to water. So this is related to both the surface chemistry and the bulk chemistry. And we will, in subsequent lectures, we will talk a lot more about this because for drug delivery systems, it's really important to understand whether we have bulk degradation or surface degradation, because that will change the release kinetics for the drug delivery systems. So polymers that degrade through hydrolysis, so water adds across a bond and that bond breaks, are often used specifically for that ability to degrade because they'll degrade in the body. These reactions can be acid catalyzed, base catalyzed, and sometimes enzyme catalyzed. If water can permeate into the bulk of the material, then it's not going to be a surface phenomenon. It's going to degrade throughout the bulk as well. And we will discuss that in more detail when we're talking about bulk versus surface erosion for drug delivery systems. The big thing that impacts hydrolysis and the rate of degradation of materials is the molecular structure. Okay, so the first one is bond stability. So if a bond is readily hydrolyzable, it's going to degrade faster than a bond that does not degrade readily with water. Then we move on to hydrophobicity and hydrophilicity. So if the material is really hydrophobic, it's not going to degrade as fast because the water's not going to diffuse and be as in intimate contact with that bond. It's going to inhibit degradation. In contrast, if it's very hydrophilic, it will degrade more quickly because the water is right there and it can get to the bond that's going to be degraded. Higher molecular weight means a slower degradation time. Hopefully that makes sense. Your chain is bigger, it takes longer to break it down. And then the morphology of your sample is crucial. So if you have a high degree of crystallinity of your polymer sample, you're going to have slower degradation. Degradation tends not to occur in the actual crystalline parts. So you're going to be degrading the amorphous parts and then from the surface of the crystals. And so the higher your percent crystallinity, the slower the hydrolysis. If you have a porous sample versus a solid sample, the higher the porosity, the more the water can get in, the more surface area there is, the higher the degradation rate, the higher the hydrolysis. If you have a lower TG, if you're well above TG, there's more polymer motion, more hydrolysis. Okay. When we use the term degradable in terms of polymers, often what we really mean is hydrolyzable. And we can talk about two classes of polymers, synthetic polymers versus natural polymers. The degradation rates, the morphology, all of those things can often be more easily tuned for synthetic polymers. And so a lot of times when we, the materials that we're using for controlled drug delivery, for tissue engineering scaffolds and that kind of thing, where we really want to know the degradation profile and control it, often those are made from synthetic materials. But sometimes natural materials have a bigger advantage as well. So you see more natural materials used in tissue engineering, and definitely synthetic materials are used more in drug delivery. So to talk about those factors that really impact whether a material is hydrolyzable or not, first we're going to look at bond stability. Esters, the formation of an ester from an acid and an alcohol is an equilibrium reaction. When we make a polyester, we have to drive the reaction to the right by removing water. If we put water back in, we can get the reaction to go back to the products and break the ester into the acid and the alcohol. The classic example of this are aliphatic polyesters. So polylactic coglycolide, so that's a polylactic acid, polyglycolic acid, copolymers, and the individual polymers, they're all hydrolytically unstable. They are all degradable polymers. They are often used in resorbable sutures. You can tailor their properties by changing the ratio between lactic acid and glycolic acid. That's going to dial in the percent crystallinity, and you can do a lot of and can really control the degradation rate by changing those ratios. In contrast, if we look at PET, polyethylene terephthalate, its trade name is Dacron. This, because this has an aromatic ring, that ring brings a lot of hydrophobicity right next to the ester groups. This material does not appreciably degrade in the human body. It's very stable, and that's because we've changed the hydrophobicity near the bond that we're talking about. So this is more stable, very slow to minimal hydrolysis. So this is used in vascular grafts, patches, and heart pumps, things that need long-term stability. And just to show you a little bit of the chemistry, you can have a base catalyzed polyester hydrolysis. We have an OH minus that's going to attack the carbonyl carbon, and eventually you're going to get the alcohol to pop off. And again, this is just for your reference. We're not going to go into the chemistry details too much. So we can have base catalyzed polyester hydrolysis. We can also have acid catalyzed polyester hydrolysis, and that's shown here. But in both cases, you're just taking the ester and splitting it back into a carboxylic acid and an alcohol, okay, just depolymerizing. Now let's talk about the amide bond or peptide bond. This is hydrolyzable, but it doesn't occur at an appreciable rate under conditions in the human body. So nylons are going to be used for removable sutures as opposed to degradable sutures because they're quite stable in the body. In contrast, anhydrides, polyanhydrides, but the anhydride bond linkage is very hydrolytically unstable. This will degrade quite rapidly. So it'll pop this right here. This will pop open into 2 carboxylic acids with the addition of water. And this is a very rapidly occurring reaction. And this is really important because this is a surface-based reaction, and that can really help us when we're trying to control the drug delivery, releasing a specific drug, and we want to know that release profile and have a very steady profile. So we will come back to this when we're talking specifically about surface degradation for drug delivery matrices. Ethers also can be hydrolyzed, but again, this is very slow under ambient conditions and in the human body. Urethanes, polyurethanes were originally considered to be quite biostable, but they are not as biostable as originally thought. There is slow hydrolysis, but there is some appreciable hydrolysis, and that might be into actual defects in the polymer, different linkages than the actual polyurethane. There's a lot of information regarding pacemaker lead sheaths, the insulation of the pacemaker leads, and that's been studied quite a bit. Ureas and carbonates are also, it is possible to hydrolyze them, but they don't hydrolyze at an appreciable rate. So just trying to show you the relative rates. So polyanhydrides are by far at the top of the list. They hydrolyze the fastest. Next are aliphatic polyesters, and then there's really a big change between the remainder on this list. Another way to look at it, and we've got anhydrides and esters, and they're just much, much faster than amides and any other of the bonds I just mentioned. And here are the half-lives of these hydrolyzable polymers. So you can see the half-life of an anhydride is very short. The half-life for L-polylactic acid is long, and that's why this is typically, a lot of times you're using this with copolymers. Polyamides, this is huge, right? We will talk about this paper in much more detail when we get talking about drug delivery, but this will be one that we will read and discuss as a class. So sometimes we want materials to degrade, and sometimes we want stable polymer chemistries. Olefins tend to be relatively stable. Halogenated hydrocarbons tend to be relatively stable. Siloxanes, sulfones. So these tend to be the more biostable materials, less hydrolyzable. There's a lot of biological factors that can influence hydrolysis, and pH is a big one. Now, a lot of times when we're hydrolyzing a material or a polymer, one of the things it breaks down into is a carboxylic acid. So you can have a decrease in pH at the site, and that decrease in pH can catalyze the hydrolysis, which creates more acid, which can decrease the pH, right? So these are all things you have to think about, okay? Hydrolases are natural enzymes, right? And they catalyze hydrolytic reactions. So there's proteases, esterases, so when you're using a material in the body, you have to think about the enzymes that are present and not just its pure, what's the rate it degrades in water, right? It's a little more complicated than that. The final thing we really need to consider is the influence of hydrolysis on the in vivo performance. Loss of structural integrity, that can be a good thing or a bad thing, right? If we're wanting it to degrade and release a drug, then that's what we want to have happen. But if we're expecting something to be biostable, then this is a real problem. And then we, of course, have to always consider whether the toxicity and mutagenicity, it's a hard one for me to say, of the degradation products, okay? And then finally, what I'd like you to do next is I will post this link. It is a document that will be in our shared folder. And what I would like you guys to do is there's instructions on this, but I want you guys to find a peer-reviewed article about controlled drug delivery systems. That's just something that interests you. Give me a sentence or two why it interests you. And I also would like you to find a commercial website that talks about a drug delivery system and talk a little bit about why it interests you. And after you've found those things and you put a sentence or two in on why you chose it, I'd like you to look at other students and mark the ones that you think are really interesting, and we'll try and incorporate those into class. Okay. Thank you.